Right, we're about to embark on the second walk. Scaling everything down 10,000 times, the walk yesterday scales down to 50 centimeters. In other words, everything I saw yesterday, the asteroids, the planets, and the nearest Kuiper Belt object, Quasar, fit inside a 1 meter wide beach ball. The Sun, meanwhile, which yesterday was 1 meter wide, is 100 microns across at this scale, a speck of dust. Bunched up around the edge of that 1 meter wide beach ball, we have the Kuiper Belt. Let's take a look at it at yesterday's scale. The Kuiper Belt is made of objects with stable, distant orbits around the Sun, maybe tens of thousands of objects larger than about 100 kilometers wide. The Kuiper Belt objects can be divided into two groups. The so-called classical Kuiper Belt objects orbit at a consistent distance, about 45 astronomical units. In other words, in low eccentricity orbits that are roughly circular. They don't interact with the planets, and therefore their orbits are stable. They are also known as QB10s, after QB1, nowadays known as Albion, the first such object found. All of these objects, except Pluto and Haumea, are QB10s, classical Kuiper Belt objects, of which Makemake is the largest known. Between Christmas 2018 and New Year's 2019, New Horizons did a flyby of a classical Kuiper Belt object, a QB10, now known as Arrokoth. Arrokoth is the most distant object visited by a probe with a camera. But wait, I hear you ask. If New Horizons also visited Pluto, and Pluto is farther away, then how can Arrokoth be the most distant object visited? Great question. I draw objects on the map here at their aphelion, at their greatest distance from the Sun, as opposed to their perihelion, the closest approach. At its perihelion, Pluto comes closer to the Sun even than Neptune, and it is at present closer to its perihelion than its aphelion. In other words, Pluto's orbit is highly eccentric. Such an orbit would normally be perturbed by the gravity of Neptune, sending the object hurtling into outer space, or indeed into the Sun. Pluto, however, orbits exactly twice for every 3 orbits of Neptune, and as such, never comes close enough to Neptune to be affected by its gravity. There are many such objects that orbit in a 2-3 resonance with Neptune specifically, the so-called Plutinos after Pluto, and others with less stable orbit resonances like Haumea, which orbits 7 times for every 12 orbits of Neptune, one fewer than a Plutino would do in the same number of orbits. Together, these objects make up the resonant Kuiper Belt objects. I want to talk about Haumea very briefly. You'll recall last time I mentioned that hydrostatic equilibrium usually means an oblate spheroid, a squashed ball. Haumea, which rotates once every 3.9 hours, is spinning so fast that it's what's called an ellipsoid, or ovoid. Imagine an egg with no discernible big or little end. Moreover, Haumea is not, like almost all other Kuiper Belt objects, red, because it is covered in highly reflective water ice. In other words, Haumea is a shiny egg with rings and 2 moons that orbit very close to it, themselves in unusual and mysterious orbits. I would love nothing quite like I would love to see a photo of Haumea in my lifetime. But enough of the Kuiper Belt. Let's get walking. Today's walk will cover about 8 light years. At this scale, we will traverse the Oort Cloud and reach the nearest stars. Like I said, the Sun is 100 microns across at this scale. Within an arm's length, we have Eris, which is not a Kuiper Belt object. It is rather what's called a scattered disk object. At this scale, 1/5 of a micron across the width of a bacterium, about the same size as Pluto, Eris is the most massive of the dwarf planets, and the 9th most massive object orbiting the Sun, after the planets. About the same distance we have Gong, like Eris, a scattered disk object. Unlike the Kuiper Belt objects, the scattered disk objects lie in orbits that are not stable, because they are perturbed by the gravity of Neptune. Like the Kuiper Belt objects, they can be divided into 2 groups. At around this distance, we find the aphelia of the scattered disk objects proper. And at about 1.3 meters, we get to the heliopause. This is basically the edge of the heliosphere, where the interplanetary medium, dominated by the solar wind, mostly ionized hydrogen, is overcome by the interstellar medium, dominated by cosmic gamma radiation. Voyager 1, which was launched in September 1977 and is still transmitting, it will probably die in 2021, crossed the heliopause at 121 astronomical units on the 25th of August 2012. And we know that it did because the data that it transmitted back to us changed at this point, confirming many of our theories of the interstellar medium. Voyager 2, which was launched in August 1977, crossed at 119 astronomical units on 5 November 2018. Voyager 2 is also still transmitting, it will die this year. When Voyager 2 crossed the heliopause, it sent some very strange data back to us, suggesting that the density of the interstellar medium is greater than that of the interplanetary medium. Still a bit of a mystery, but maybe one day we will know. New Horizons, which was launched in 2006, is about 50 astronomical units away. It's still in the Kuiper Belt. It will cross the heliopause in 2043. We take our first steps, and we get to Sedna at 10 meters distance. Sedna is 70 nanometers wide at this scale, about the size of the Zika virus. Its perihelion is less than a meter at this scale, but its aphelion is just under 1,000 astronomical units. This is a highly eccentric orbit, and it's a very mysterious orbit because everything else being equal, such an orbit should not form naturally in our solar system. Indeed, there are a number of other objects that orbit about this distance, the so-called detached objects, which orbit not only at this distance, but unusually in roughly the same direction and at the same angle. This is extremely unlikely to have happened by chance. A study estimated the probability of this at 0.25%, 1 in 4,000. So why might this be? So far, no one knows. Of all the theories proposed, the most widely accepted is that there is a very massive object, roughly the size of Uranus or Neptune, orbiting in the opposite direction. Presently near its aphelion at about 1,200 astronomical units, halfway to the Oort Cloud. Too far away, in other words, to see with anything other than the most powerful telescopes. For now, the so-called Planet 9 is entirely theoretical. It is one of many explanations for the unusual behaviour of the detached objects. Bit of a mystery, but we will likely know whether Planet 9 exists or not inside the next decade. At about 20 meters, we get to the Oort Cloud. What is the Oort Cloud? In a word, the Oort Cloud is a vast sphere around the Sun, sparsely populated by icy, rocky objects, out to the edge of the Sun's Hill sphere, the region inside which the Sun's gravity dominates over that of the rest of the galaxy, about 3 light years away. The Oort Cloud is enormous. It is annoyingly large. It's ridiculously large. The largest objects in the Oort Cloud are 20 kilometers in diameter, so 1/50th of a dwarf planet. At this scale, that's about 1.4 nanometers. For comparison, DNA is 2.4 nanometers wide. On this street in the real world, there are about 1 million dust particles per square meter. The total volume of the Oort Cloud at this scale is about 4 cubic kilometers, so 4 quadrillion dust particles all told. But the total number of Oort Cloud objects is likely in the trillions, in other words, 1,000th the number of dust particles. Meanwhile, dust particles are measured in microns, whereas Oort Cloud objects at this scale are measured in nanometers. In other words, there is 1 trillion times more volume taken up by stuff in the air that I am breathing as I walk down this road than there is Oort Cloud objects in the Oort Cloud. The total mass of all of the Oort Cloud is estimated to be about 5 times that of Earth. It is that sparse. So why is the Oort Cloud interesting? Well, in a word, because it's where comets come from. Due to its incredible sparseness and low mass, we're not able to observe the Oort Cloud directly. It is rather implied by the maths and by observations of comets. So what are comets? Comets are a bit mysterious. Every new discovery seems to raise more questions than it answers. In short, a comet is composed of a comet nucleus, which is basically a dirty snowball, composed of rock, dust, and frozen gas. As the comet enters the heliosphere, the gas sublimates, creating what's called a comet coma, a massive gas cloud, a bit like an atmosphere, but very hot and much, much larger than the comet itself. Comet Holmes, for example, discovered in 1892, had a coma larger than the Sun when it returned in 2007. As the comet careens through the heliosphere, it starts to crumble. The gases stream away from the nucleus in the direction of the solar wind, and the comet grows two tails, one of gas, which points directly away from the sun, and one of dust, which trails behind the comet in its wake. On the 6th of August 2014, Rosetta, which was launched in 2004, landed a module called Philae on comet 67P Churyumov-Gerasimenko, or 67P for short. Philae discovered 16 complex organic compounds on the surface of the comet nucleus, including the amino acid glycine, a protein precursor and one of the basic elements of life on Earth. More likely than not, the first life on Earth, in the form of the first complex prebiotic compounds, was seeded by a comet or something like it, and so probably too was the first water. And indeed, the archaeological record shows that life and water both appear on Earth at about the same time, 4 billion years ago. Bit of a mystery. Maybe one day we will know. At 1 kilometre we reach the Blue House roundabout, and this is the edge of the Oort Cloud. Voyager 1, the fastest moving man-made object in history, at 35,000 miles per hour, or 16 kilometres per second, will reach the inside of the Oort Cloud about 300 years from now, and it will pass through and out the other side in about 30,000 years, almost certainly never colliding with an Oort Cloud object. Let's keep cruising up the road here. Let's go see some stars. This is all the interstellar medium here. It's not clear if there's anything here, though it's entirely possible that other stars have Oort clouds which reach out and touch our own, in which case we would now be moving through the Alpha Centauri Oort cloud. As we get to Regent Point, we reach Proxima Centauri. Proxima Centauri is a red dwarf. It's 15 microns wide at this scale. For reference, Jupiter is 10 microns across this scale. So Proxima Centauri is not much larger than Jupiter. On the 17th of December 2020, a couple of weeks ago as of recording, the Parkes Radio Telescope in Australia detected a radio signal which appears to have originated at or near Proxima Centauri. The signal appears to be artificial, like telecommunications signals on Earth. Now known as BLC-1, Breakthrough Listen Candidate 1, the signal is presently unexplained. Bit of a mystery. Maybe one day we will know. Cruise on a little bit further to Regent Center, and we get to Alpha Centauri. Alpha Centauri is a binary star system. The two stars are very similar to our Sun, about the same size, 100 microns wide, and similar sort of mass and temperature. Alpha Centauri A is a little bit larger. It's a G25 star, almost exactly the same as our Sun. Alpha Centauri B is slightly smaller. It's a K15 star, so slightly cooler. In fact, Proxima Centauri is gravitationally bound to Alpha Centauri, making the whole a trinary system. Keep on walking, and we get to the suburbs, and ultimately to this rather fancy part of town, specifically to Fencer Hill Park, which is a walled estate, mansion-y looking thing. Here is where we find Barnard's Star. Barnard's Star will be the closest star to our solar system in some tens of thousands of years' time. At this scale, 20 microns wide, just over 1/10 the mass of the Sun, and about 100 times the mass of Jupiter. Keep on walking. Somewhere in suburbia, somewhere around here, we get to Lumen 16. Lumen 16 is a binary brown dwarf system. Both of the Lumen 16 brown dwarfs are about 9 microns wide, in other words, smaller than Jupiter, but they are both about 30 times its mass. That's about all we're going to see on this walk, but there are some stars a little bit further away as well, but we shall talk about them next time.